When we gaze up at the star-filled sky, an inevitable question rises in our minds. How big is the universe? Does this infinite expanse have an end, or does it stretch on forever like a boundless cosmic ocean? Thinking about the vast scale of the universe takes our imagination on an extraordinary journey. A journey where Earth appears as nothing more than a tiny speck against the overwhelming grandeur of the cosmos. In this video, we dive deep into this profound question and explore the astonishing scale of the universe together. Join us on this cosmic voyage as we uncover the secrets hidden within space-time and gain a new understanding of our place in this endless expanse. To measure distances in the universe, we first need to know how fast light travels. About 300,000 kilometers per second. This is where the idea of a light year comes in. The distance light travels in a single year. For example, the closest star to us after the Sun, Proxima Centauri, is about 4.3 light years away. As we look farther into the universe, distances grow enormous. That's why we use incredibly precise tools like space telescopes to observe the light from distant galaxies. But light doesn't travel through a static space. Space itself is stretching. It's as if light is moving across a rubber sheet that's expanding. Because of this, the objects we see are actually much farther than they appear. We might be seeing light that has traveled 13 billion years to reach us. Yet due to cosmic expansion, that galaxy is now over 40 billion light years away. So how do we determine the size of the universe? By measuring the oldest and farthest light that reaches us, while remembering that we're observing an expanding universe. To talk about cosmic distances, we rely on special units. Kilometers and meters simply aren't enough. This is why scientists use the light year, a unit of distance. Light travels at 300,000 kilometers per second, fast enough to circle Earth 7 times in a single second. With this unit, cosmic distances become easier to grasp. For instance, the distance from Earth to the Sun is 8 light minutes. The light we see from the Sun left it 8 minutes ago. Proxima Centauri, at 4.3 light years away, would show its explosion to us 4.3 years after it happens. Let's explore what distances really mean in the cosmos, starting from the closest regions and gradually moving outward. Before we need light years, kilometers are already too small. So astronomers use the astronomical unit. AU, 1 AU, equals 150 million kilometers, the distance from Earth to the Sun. Earth to Mars at closest approach, 0.5 AU, Earth to Pluto, about 40 AU edge of the solar system, about 100,000 AU. Even with the fastest spacecraft we have today, reaching the closest star to us would take around 70,000 years. Reaching another galaxy, far beyond our current abilities, beyond the solar system, lies the Milky Way, a spiral galaxy with at least 100 billion stars. Our distance to the Milky Way's center is 27,000 light years, where the supermassive black hole, Sagittarius A, resides. The galaxy itself is about 100,000 light years across. A beam of light would take 100,000 years just to cross it. The Milky Way is part of a small family of galaxies called the local group. Its nearest large neighbor, Andromeda, lies 2.5 million light-years away and is slowly moving toward us. In about 4 billion years, the two galaxies will merge into a gigantic new galaxy. The local group belongs to a larger structure called the Virgo supercluster, roughly 100 million light-years wide. But even that is part of something greater, the Laniakea supercluster, spanning around 520 million light-years. At the largest scales, we reach the boundary of the observable universe. The most ancient light we can detect comes from the cosmic microwave background, CMB, about 13.8 billion light-years away. Yet, because of cosmic expansion, that region is now roughly 46.5 billion light-years from us, and that marks only the edge of the observable universe. Beyond it may lie galaxies, structures, or even entire realms we may never be able to see. This raises a profound question. How big is the entire universe, really? Is what we see everything, or just a tiny fragment of something far greater? Here is where scientific theories come into play. Ideas that have challenged and fascinated scientists for decades. The cosmic microwave background, CMB, comes from light that began its journey about 13.8 billion years ago. But as we mentioned before, because the universe is expanding and galaxies are constantly moving away from each other, those regions are now roughly 46.5 billion light-years from us. That means the radius of the observable universe is about 46.5 billion light-years. If we draw a cosmic sphere around ourselves, its radius would be 46.5 billion light-years, and that's only the boundary of what we can see. The full diameter of the observable universe is about 93 billion light-years, but that's just the part we're able to observe. So the real question is this: does the universe itself have an edge? Some theories suggest that the universe has no boundary at all, that beyond the observable horizon, galaxies continue endlessly, stretching on without limit. Certain scientists, based on measurements of the CMB, argue that the universe is flat, like an enormous sheet of paper. If the universe is flat, it has no curvature that would cause it to fold back on itself. It wouldn't behave like a sphere. So in that case, it could extend forever. Another idea: a finite universe with no edge. This theory proposes that the universe is finite, but still has no boundary. Similar to the surface of a sphere, if you walk in a straight line across Earth, you never reach an edge. You simply loop around. It's a fascinating analogy. On Earth, living in 2 dimensions on the surface, we can't escape without entering a 3rd dimension. Likewise, to go beyond our universe, we may need to move through dimensions beyond space-time itself. The multiverse hypothesis. Another theory you may find intriguing is the multiverse. Some scientists believe our universe might be just one of infinitely many. This idea comes from cosmic inflation. According to this model, in the first instant after the Big Bang, the universe expanded faster than the speed of light. Some researchers think this inflation could have happened in multiple separate regions, creating entirely different universes. These universes might have different physical laws, different structures, or even completely different forms of matter. This idea is supported by certain equations in quantum physics and string theory. Another theory, the ever-expanding universe. This one states that our universe is expanding at an accelerating rate and will never stop. This acceleration is driven by dark energy, which makes up about 70% of the universe and acts like a repulsive force, pushing galaxies farther apart. If this expansion continues, distances will become so vast that nothing will remain visible. Every galaxy will fade into darkness, as if the universe dissolves into a cosmic night. If this theory is true, the universe will continue growing forever, unless something with the power of creation itself brings it to a halt. But a crucial question remains. Why can't we see beyond 46.5 billion light years? What limit are we facing? That's where the cosmic horizon and the expansion of space come in. What is the cosmic horizon? It's essentially the limit of our vision. The farthest distance from which light has had enough time to reach us. Anything beyond this boundary is invisible, not because of an obstruction, but because its light simply hasn't arrived yet, and maybe never will. Since the universe is only 13.8 billion years old, we can only see objects whose light has had that much time to travel. But because space itself is expanding, the regions that emitted that ancient light are now far beyond 13.8 billion light years. In fact, around 46.5 billion. That's why we say the observable universe has a radius of roughly 46.5 billion light years. Why can't we see beyond that? Because light has a speed limit. Any object beyond the cosmic horizon is so far away that its light is either still on the way or will never reach us at all. Why never? Because after the Big Bang, space began to expand. Not galaxies moving through space, but space itself stretching. Imagine drawing dots on a balloon and inflating it. The dots spread apart without moving on their own. The expanding space increases the distance that light has to travel. If that distance grows faster than light can cross it, then the light will never reach us. At extremely large scales, the expansion of space is faster than the speed of light. So anything far enough away is receding from us so quickly that its light will forever remain out of reach. Beyond the cosmic horizon lies a realm of complete unknown. Not because something blocks the view, but because the universe expands too quickly for light to bridge the gap. So, how big is the actual universe? The honest answer: no one knows. We can estimate the size of the observable universe, about 46.5 billion light years in radius. But this is only a tiny fraction of the entire cosmos. The universe could extend far, far beyond, or it might even be infinite. The only certainty is that we will never see beyond the cosmic horizon.